All right, so now that we finished Unit 3A, we're going to go ahead and kick off Unit 3B, which is going to be all about graphing quadratics. So I'd like you to start a brand new table of contents. It's Unit 3B, Graphing Quadratics Table of Contents, and the very first section, which we're going to have notes on today, is going to be 3.6, Graphing in Standard Form. Once you have that table of contents ready, make sure, again, remember that the back of that table of contents is going to be your warm-ups page. You can leave yourself a couple of pages if you feel like you're going to need more room, but we're going to go ahead and have that table of contents ready. Once you're finished with that, we're going to be ready to go ahead and start our notes. So the notes are going to be 3.6, Graphing in Standard Form. Okay, I'm just going to use markers, but now I feel like they're going to be too blurry, so we'll use pencil instead. All right, so here we go. We're going to start off talking about graphing in standard form just by talking about some properties of quadratic functions before we talk about just the ways to graph them. Yesterday we talked about how to match graphs and their equations based on their zeros. So we started with the zeros, and then we went to factored form, and then we found the standard form equation. But not every quadratic graph is going to have zeros. If it doesn't touch the x-axis, we aren't going to have any zeros at all. So we have to have some other way to take equations from standard form and put them on a graph. So first and foremost, let's talk about standard form properties. I feel like this is way too shaky. We'll figure it out. Okay. Standard form properties. And again, a standard form quadratic equation is ax squared plus bx plus c. So that's our standard form equation. One of the most important things about this standard form equation is that it's possible for a, b, and c to be absolutely any numbers as long as a does not equal the number 0. So it's okay if b is 0 and we don't have a middle term. It's okay if c is 0 and we don't have a last term. But if a is 0, we won't have an x squared and it's not going to be a quadratic anymore. So we have a, b, and c. A cannot be 0. Now there's going to be a couple things that we can tell just based on these letters. So first and foremost, a, the number out in front that's being multiplied by our equation, being multiplied by x squared. This a is going to help us determine the shape of our quadratic graph. Just like we learned about with transformations, if we have a negative out front, it's going to invert the graph and flip it upside down. So if a is a positive number, we're going to have a face-up graph, and if a is a negative number, it's going to be a face-down graph. So let's go ahead and write that down. If a is greater than 0, the parabola is going to open up. We call that concave up. So if a is greater than 0, the parabola is concave up. And one of the ways to remember what that's going to look like, I'm going to put it in parentheses off to the side, up like a cup. Makes it easy to remember. So if a is greater than 0, so if it's 1, 2, 17, doesn't matter, even 1/2, it's still greater than 0, we're still going to open up like a cup. Now if a is less than 0, if a is a negative number, remember if we see that negative out front, just like we saw in the activity yesterday, if we saw a negative out in front of our factors, we knew that the graph opened down. So it's concave down. So let's go ahead and write that over here. If a is less than 0, the parabola opens down, which is what we call concave down. Is concave down, and one of the ways to remember that one is like a frown. So if a is less than 0, parabola is concave down like a frown. So it's going to be sad face. All right. So now we know the shape of our parabola, if it's going to open up or if it's going to open down. Up next, another thing we can tell just by looking at the standard form equation, using these letters A, B, and C, we're going to be able to find out where our axis of symmetry is. So the axis of symmetry, remember, is that line that cuts a parabola exactly in half, where we could fold it and it would match on either side. So an axis of symmetry is the line, and I'm going to underline line here, because I want to make sure that we know that it is a straight line that technically continues forever. And this straight line comes from an x equals number. It's a straight up and down line. So this line exists everywhere that we have an x value on our graph. And the x value for our axis of symmetry is actually going to come from these values inside our equation. We're going to get it from negative b over 2a. That probably looks a little bit familiar because we know we have a negative b and a divided by 2a in our quadratic formula. So hopefully that makes this a little bit easier to remember. If we just take the negative b and divide it by 2a, we're actually going to get the axis of symmetry for our graph. Now, we also know that the axis of symmetry for a parabola runs straight through the vertex. The vertex is that highest or lowest point, depending on the shape of our graph. So this x value, x equals negative b over 2a for the axis of symmetry, that's actually also the x value for the vertex of our quadratic. So instead of starting with the zeros to graph it, we're going to start with the vertex. So let's go ahead and write that about the vertex. So the vertex is a point, and I want to emphasize that one as well. It's a point. So the axis of symmetry is an entire line, but the vertex is just one point. It's going to have the same x value as the axis of symmetry, negative b over 2a, but if I plug in that number, negative b over 2a, if I plug that into my equation, I'll be able to get the output that goes with it. So this is an x value, and it comes from this same x value here. And in order to get the y value that goes with it, to find the rest of my vertex, I have to plug this number into my equation. So I don't know what specifically my equation is. So what I'll say here, and forgive me if that's a bit confusing, but what I'll say for my y value, remember that's the output. I plug in an x value, it gives me out a y value. It's just f of whatever that number is. So negative b over 2a is going to be a number. If I plug that number into my equation, it will give me the y value that finishes my vertex. And we're going to see some examples of that, and it'll be a little bit less confusing. There are a couple more things that we can see from just this form of the equation. One of them is going to be my y-intercept, the y-intercept, which can be very helpful when we're graphing. So a y-intercept is where it hits the y-axis, and it hits the y-axis when my x value is 0. So if I plug in 0 to a standard form equation, this x squared will become a 0, and that will disappear. This x will become a 0, and that will disappear, and all I'm left with is the number c. So my y-intercept is actually always going to be 0, comma, whatever that c value is. So if this is a +4, then my y-intercept is at 0,4. If that's a -7, then my y-intercept is at 0, -7. Okay. We have one new concept here that's coming up about these parabolas that I want to make sure that we mention, because it's going to be one of the most useful things that we're going to use when graphing these. So we're going to use our vertex a lot. We're also going to be using the slope of our parabola. But a parabola, because it's a curve, it has changing slopes everywhere. So we're not actually looking at just the number of the slope. Instead, we're looking at how the slope is being adjusted by our equation. So what we're going to say that is that this equation, specifically this a value in front, is going to be multiplying our slope and changing our outputs by whatever number that is. So I'm going to write it like this. Slope outputs are multiplied by a. So in order to get a good idea of what that means, let's go ahead and take a look at the standard slope pattern for a parent function parabola. So I'm going to write standard slope pattern Okay. So if I think about a standard parabola, this is y equals x squared. First and foremost, my a value is the number in front of x squared. It's just 1. But my b value is 0. And my c value is also 0. Those have disappeared. All I'm looking at is just x squared. So I know that x squared starts at 0, 0. And if I wanted to show that by using my vertex, negative b is just 0, divided by 2 times a is just 1. So 0 divided by 1 is just 0. If I plug in 0 to this equation and square it, I get 0. So my vertex is at 0, 0. Now my standard slope pattern, we think about slope as rise over run, but what we're going to do when we're graphing here is we're going to look at the run first, because the run is the x values, and I know that I can plug x values into my equation and figure out how high up it goes. So if I go over 1 on my parabola, and it doesn't matter which direction, because remember, this is an axis of symmetry, so it's going to have the same shape this way as this way. So if I go over 1, let's go ahead and say I'm moving to the right one. If I plug in the number 1 to this equation, I will square it. I will go up 1. So let's say this is up 1. So over 1, up 1. And again, if I go to the left one, same thing, over 1, up 1, right? That's my first pattern. But these aren't straight lines because this is a parabola. So I also have over 2. Let's see how far I usually go there. Again, over 2 means I'm plugging in 2 as an x value. I'm going to square that number, 2 squared. That means I have to go up 2 squared, which is 4. So I have to go up 1, 2, 3, 4. And I go up all the way over here. So over 2, up 4. And again, if I go 2 to the left, same thing's going to happen. I'll have to go up 4. So now we can kind of see a pattern happening. And this pattern will continue. If I go over 3, I'll go up 9. These are all the squared versions. This is all the outputs that have been squared from the inputs that I'm plugging in. And it makes a parabola shape. So this is the standard form that we're going to be using. Now the a values from my equation are going to change these outputs by multiplying them by a number. So if my a value is 2, then all of these outputs are going to be doubled. Instead of going up 1, I'm going to multiply that by 2, and I'm going to go up 2. Instead of going up 4, I'm going to multiply that by 2, I'm going to go up 8. Instead of going up 9, I'm going to multiply that by 2, I'm going to go up 18. So we're going to have really big changes based on whatever number is in front of x squared, and that will help us graphing a lot. Okay. So we're going to use this to graph some things in just a second, but first I wanted to talk a little bit about the domain and range of these quadratic functions. That way when we go ahead and graph them, we can look at all of the features all at once, because domain and range is not new for us. Y-intercepts are not new. We've talked about vertexes and axes of symmetry. We even mentioned concavity before. So I know this is a brand new thing, and I know these formulas are new. Let's just look at domain and range real fast, because there's some really, really helpful patterns. And then we'll look at some examples of actually graphing some of these quadratics, okay? All right, so let's talk about domain and range. So the nice thing about my parabolas is that I will always be able to plug in any x value that I want to. It will continue going to the left forever, and it will continue going to the right forever. So my domain is always going to be infinite. I'm going to go back to writing my domain and range in set notation. If you'd like to use interval notation, it's up to you, but I want to make sure we don't forget how to use and read set notation as we go. So the set notation is domain is the set of x values such that x is all real numbers. And that R with a line through it means all real numbers. So domain is the set of x values such that x equals all real numbers. So we have our domain, and our domain will always be all real numbers. It's the range that will change. So to find the range, all we have to do is look at the vertex and the concavity. It's actually pretty simple. So we have a U shape, or it could be upside down, like a frown, which means we're either going to always have a maximum or a minimum. Let's look at a maximum first. So a maximum will happen when a graph is concave down, like a frown. So a very simple sketch of that, down like this. There's our quadratic. And if we're down like a frown, this top point here, this vertex, is going to also be the maximum height, because it's not going to get any higher than that. We're going to go up to that point, turn around, and go back down again. So the range of a function that's concave down is going to be all the y values that are smaller than that vertex y value, right? So the range is y is less than or equal to the number that is the y value of the vertex. So let's look at an example. Let's say that this is a quadratic like this. Let's say this point is 1, 4, whatever, doesn't matter. But if I have an equation that looks like this, here's my quadratic. The domain is going to be the set of x values such that x is all real numbers. And the range is going to be the set of y values such that y is less than or equal to whatever this highest point was. This highest point is the y value of my vertex. My vertex is at 1, 4. All I have to do is find that y value, that number 4. Y is less than or equal to 4. That's it. Easy peasy. If we want to write this generically, we could say that our range is going to be the set of y values such that y is less than or equal to f of negative b over 2a. So whatever my equation is, if I don't know what the graph looks like, if I don't know where that vertex is, I can find that point just by taking the x value of my vertex and plugging it into my equation and seeing what that corresponding y value is. So f of whatever that x value of my vertex is. So I can use my standard form equation to find my maximum point. And again, that's going to be when it's concave down, where a is less than 0. Now we also have a situation where we could have a minimum. And a minimum would happen when my graph is upside down from that. So when my graph is concave up. And remember, up like a cup, so it looks like this. So if my graph is concave up, it means that this bottom point here where my vertex is, that's the minimum point of my graph. So we're going to keep going down until there, then turn around and go back up again. We're never going to get any lower than that. So again, my domain is still going to be the set of all real numbers, but my range is going to be my y values that are bigger than that y value of my vertex. Y is greater than or equal to the number that is the y value of my vertex. So let's go ahead and take a look at a little example. Maybe we have this guy over here, and maybe it goes down like this, and maybe my vertex is at 0, -3. I don't know, doesn't matter. So that could be a -3 right there. If I was going to find the domain and range of this function, my domain is going to be the set of x values such that x is all real numbers. That's the same. But my range is going to be the set of y values, right here, y values that are bigger than that number. So y is greater than or equal to the y value of my vertex, -3. So as long as I know my vertex and I know what concavity I have, I'm going to be able to find my range. My range for this one is going to be the set of y values such that y is greater than or equal to f of -b over 2a. So this one is concave down, a is less than 0. This is concave up, a is greater than 0. So if I know what my concavity is and the y value of my vertex, I can find my range. Awesome. Okay. Let's go ahead and actually look at some examples and see if we can figure out and pinpoint some of these key features based on a standard form equation. So we're going to start with this guy. Oh, first let's write down one key point. I don't want to forget. Let's put a big star next to this so we can remember. When we are graphing quadratics, so graphing quadratic steps. Let's make sure that this is easy to find in your notes. The very first thing we're going to do is going to be to graph the vertex. And then the next thing we're going to do is we're going to use the A value and those slope outputs like we talked about for a second on the other page. So if I want to graph a function, a quadratic function, I'm going to start with my vertex, and then I'm going to be able to use those A values from my slope outputs in order to finish graphing. So let's look at an example here. First and foremost, here's our example. F of x is x squared minus 4x plus 6. The very first thing I want to do is identify my a, b, and c values. So a equals the number in front of x squared, which is 1. B is the number in front of x, which is -4, the entire thing. And c is the number all by its lonesome over here, which is the number 6. All right. We have our a, b, and c values. Let's try and figure out a couple of things before we go forward and graph this. First and foremost, is this concave up or down? Well, if I want to figure out if it's concave up or down, I just have to look at my a value, whether it's bigger than or smaller than 0. So a is the number 1. That means a is bigger than 0. That means this is concave up like a cup. Up next, let's look at the axis of symmetry. This is a nice one to calculate first because this is going to give us the x value of our vertex. So the axis of symmetry, we can find that by doing -b over 2a. That's all we have to do. X equals -b over 2a. So let's plug in our equation over here. -b. B is the number -4. It's important that we do -4. Just like plugging into the quadratic formula, make sure you do the opposite here, okay? So -b over 2 times a. There we go. So -4 becomes a +4. 2 times 1 on the bottom is just 2. 4 over 2 is 2. So my axis of symmetry is the line x equals 2. And that is also the x value of our vertex. So up next, let's go ahead and find that vertex. The vertex takes the x value from my axis of symmetry. So my vertex is actually 2. That's the x value. And then I just have to find the y value. So we had written it in our notes that we had to take f of -b over 2a. But instead of plugging all of these in again, I already know what -b over 2a equals. It equals the number 2. So all I have to do is find f of 2. And that's it. That's my vertex. So let's go ahead and take a look at this equation and see if we can find the f of 2 value. Here's my function f of x. If I want to find f of 2, I just have to plug 2 in here and here. So we're going to go ahead and find f of 2. We're going to take 2 and square it. And then we are going to subtract 4 times 2. And then we can add 6. So f of 2 is 4. 2 squared is 4. Minus 8 plus 6. 4 minus 8, that's -4. -4 plus 6 is +2. So my vertex is actually at the point 2, 2. Awesome. All right, let's figure out, just for fun, what's that y-intercept? Now remember, my y-intercept is just 0, c. So my y-intercept, if I plug in 0 for x, c is just 6. So 0, 6. That was fun. Okay. my slope multiple. Remember, we're going to have to use this to actually graph it. So my slope multiple is a. So here it's the number 1. So we normally go over 1, up 1. So what I'm going to write is up 1 times whatever this multiple is. In this case, the multiple is just the number 1, so we're not changing things, but we will see an example where it does change based on this number. So over 1 and up 1. We can also go over 2, up 4 times 1, and then etc., etc. We only really have to graph a couple points to do our parabola. Let's find our domain and range before we even look at our graph, and then we will be able to sketch this. So the domain of my quadratic function will always be all real numbers. So domain is a set of x values such that x is all real numbers. That one's always going to be easy. We can plug in any x value we want, no matter what. And then our range comes from our concavity and our vertex. So this is either less than or equal to something or greater than or equal to something. We said this was concave up like a cup, which means we have this minimum point down here, and our y values are all going to be bigger, which means y values have to be greater than or equal to the y value of our vertex, which is 2. That's it. We have our range. Now this is going to be a minimum. I'm going to go ahead and label that. Because we are concave up, we're going to have a minimum. As soon as you know you're concave up like a cup, you know that you've got a smallest point, something you can't go lower than. So we have way more information than we actually need to go ahead and graph this guy. All I need to actually graph it is just my vertex and my slope multiple. But I just wanted to show you how just looking at an equation itself, we can find all of this other information, even if I don't already have the graph. So I do want to go ahead and sketch a graph of this, and if you could please sketch this in your notes as well. Let's see. Excuse me. So step 1, graph the vertex. My vertex is at the point 2, 2. I'm going to go ahead and say that each line on my binder paper is 2 units. So if I go over 2 and up 2, that's my vertex right there. Now, it says after I graph my vertex, I have to use the a and slope outputs. So that's when I'm looking at this. Typically, when I graph a standard form parent function quadratic parabola, I go over 1 and up 1. Here I'm multiplying this output by 1, so I'm not actually changing it. So I'm still going over 1 and up 1. So from my vertex, if I go over 1 point, I should also go up 1 point. So over 1, up 1. And here, if I go to the left 1, I should still go up 1. So we can see it's starting to take on that parabola shape. Let's do one more, just to make sure we have a good idea of what the shape is. If I go over 2 from my vertex, I should go up 4. And again, we're just multiplying that by 1, so it won't change. So if I go over 2 from my vertex, over 1, 2, I should go up 1, 2, 3, 4. Ooh, all the way up there. There we go. So if I go over 2, I should go up 4. And again, we can do that on the left as well. From my vertex, if I go over 1, 2 to the left, I should go up 1, 2, 3, 4, right there. So now we can really see that quadratic shape, that parabola shape. Now this point here, I could have plotted to begin with. This is where it touches my y-axis. This is my y-intercept, and I already said it happened at 0, 6. Let's confirm that's true. 1, 2, 3, 4, 5, 6. Yep, that's where I touch my y-axis. So I can see that it is concave up like a cup. I can see that I have a minimum point right here. That is at my vertex. I can see that my range is all the y values bigger than the number 2. It goes up like that forever. So everything we were able to tell just from the equation, I can tell is true by looking at my graph. It's a good way to check my work. But all I needed to actually graph this was just my vertex and my slope multiples to figure out how far over and up I had to go. All right. So let's go ahead and take a look at one more example together. This one is negative 2x squared plus 4x plus 5. Let's go ahead and see if we can do some of these same things with this example. So, first and foremost, a equals the value in front of x squared, which is negative 2. B is the value in front of x, it's just the number 4. And C is the number 5 all the way at the end. Let's go ahead and find some of these attributes. First and foremost, concavity, up or down. We look at our A value right here. That negative 2 is less than 0. A is less than 0, which means I'm concave down like a frown this time. Let's look at our axis of symmetry. I'm going to label it AOS. The axis of symmetry, again, is going to happen at negative b over 2a. So that is going to be negative b is just the number 4, over 2 times a. A is the number negative 2. I have to make sure to get the signs in there. On the top, I have negative 4, and on the bottom, 2 times negative 2, I have another negative 4. So negative 4 divided by itself, my axis of symmetry actually happens at the number 1. And again, this is a line, so this happens at x equals 1. That's my axis of symmetry. And 1 is now the x value of my vertex. So let's go ahead and label that vertex. So my vertex happens at 1, comma, f of 1. So all I have to do to finish finding my vertex is take the number 1 and plug it into this equation. So let's go ahead and do that. F of 1 is going to be negative 2 times 1 squared plus 4 times 1 plus 5. So negative 2 times 1 is just negative 2 plus 4 plus 5. So 4 plus 5 is 9, minus 2 is 7. So my vertex is going to happen at 1, comma 7. All right. Let's find my y-intercept just for fun. Y-intercept is going to happen at 0, comma C. C is just the number 5. So that's done. That really challenges us a bunch. Okay, now we'll look at our slope multiple. I'm just going to call it slope multiple. So we're going to take our slope outputs and multiply them by a. So I'm going to multiply the slope that I get from my function, whatever my outputs are, I'm going to multiply those by a, which is negative 2. So normally I go over 1, up 1, but I'm going to multiply that by negative 2. So what that means is that instead of going up 1, I'm going to go up negative 2, which isn't really up at all. Instead of going up, I'm moving in the negative direction. So as soon as this happens, and I go up a negative number, what I'm actually doing is going down 2. This is where our down concavity comes from. Instead of moving over and up, I'm going to move over and down and end up down like a frown. So let's look at the next one. Over 2, up 4, except I'm going to multiply that by negative 2, and now all of a sudden I'm moving up 4 times negative 2, which is negative 8. If I move up negative 8, it actually means that I move down 8. So over 1 down 2, over 2 down 8. Big change there. Let's do our domain and range real fast, and then we'll sketch a graph of this. So our domain is always going to be the set of x values such that x is all real numbers. That's nice and easy. And the range, again, depends on our concavity. It's the y values such that y is either greater than or less than a number. So we're concave down like a frown, which means we're going to have a maximum point, and our range is going to be the y values that are smaller than that point. So y has to be less than or equal to the y value of our vertex, because that's our maximum. So y has to be less than or equal to 7. And that will be a maximum because we have a concave down graph. So let's go ahead and sketch a picture of what that graph looks like. All right. So again, in order to graph this, I don't need all of this information. This is just exercise and practicing figuring out what that critical information is. But the stuff that I do need, the vertex and the slope multiple, that's where my graph is going to come from. So let's start by graphing that vertex. My vertex is at the point 1, 7. So if I go over 1, I go up 1, 2, 3, 4, 5, 6, 7. All the way up there. There's my vertex at 1, 7. Okay? All right. My vertex is at 1, 7. Now I use my slope multiples to figure out what the rest of my graph is going to look like. Normally, I go over 1, up 1, but I have my slope multiple, so I'm going over 1, down 2 instead. I multiplied it by that -2. So over 1 to the side, down 2, like that. Let's go ahead and do that on this side as well. Over 1, that brings us back to our y-axis, down 2. So from our vertex, over 1, down 2. This should be the same as our y-intercept. Let's go ahead and check. My y-intercept is 0, 5, 1, 2, 3, 4, 5. Yep, we're on the right track. So we did our over 1, down 2. Let's go ahead and go over 2 and down the next number. So again, when it says over, it means from the vertex. So I'm going to go over 2 for my vertex. Over 1, 2. I need to go down 8. So I'm going to move over 2 and go down 1, 2, 3, 4, 5, 6, 7, 8, all the way down here. And now on this side, again, from my vertex, I can go to the left 1, 2, and down 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so now we can really see that quadratic shape, that parabola. There we go. So to draw that graph, all I needed was my vertex and my slope multiple, okay? All right. I do have one more problem that I would like you to try and work on. I'm going to put the problem here, and then I'll post the solution separately. So please try and work on this on your own, and then compare the solution to what I've put on Canvas if you have time. You will have a Math Excel assignment that's due Monday, depending on whether or not I come back to school on Friday based on whether or not I'm feeling better. If I'm not able to come back to school on Friday, then I'm going to extend the due date of the Math Excel assignment so I can make sure you can ask me questions. But as of right now, the Math Excel assignment that is homework tonight is going to be due on Monday morning, okay? All right, so let me put this last question on here that I'd like you to look at. So it is a word problem, so please just get it written down for me. And you don't have to write the whole thing, but it's not too long. So we have the height of a model rocket that is fired into the air is represented by h of t is negative 16t squared plus 64t. T is seconds, and h is feet. And what I'd like you to do with this problem to practice is try to find the vertex and slope multiple graph this expression and use that to find me the maximum height of the rocket. And you can do this problem in your notes. This is part of the notes for this unit, okay? All right. If you're finished with this video and it's still in class time, please work on this problem. If you finish this problem, you do have the rest of the class period to work on the Math Excel, but I know this was a long video, so thank you for taking these notes. Make sure you do the Math Excel. It's due on Monday, okay? Awesome.